Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to calculate a bound area with functions that end up having logarithmic types of integrals to worry about. So what we're going to do here is we're going to consider the function y equals tangent x, and we're going to calculate the area bound between that function and the x-axis from negative pi over 4 to plus pi over 3. Now, the first thing that we need to do is get some sort of reasonable graph of that function. So the tangent function, remember, is sine x over cosine x. And, if you're not familiar with the tangent function, there's something extremely important about it. The tangent function is asymptotic. It's got a whole bunch of asymptotes. It's got asymptotes anytime cosine x is equal to 0. Well, the cosine function, if we think about between 0 and 360 degrees, or from 0 to 2 pi, the cosine function is 0 at pi over 2 and at 3 pi over 2, or if I go backwards a little bit, at negative pi over 2. So the cosine function is 0 at minus pi over 2, plus pi over 2, 3 pi over 2, etc. And that means that the tangent function has vertical asymptotes at those points. So I went ahead and I've already kind of put dashed lines in here at plus pi over 2, and I put another one here at negative pi over 2. Right. The tangent function now, to plot it, well, let's take a look at like x equals 0. Cosine of 0 is 1, sine of 0 is 0, so the tangent of 0 is 0. And we don't need a perfect sketch for this. I'm just going to go ahead and sketch the rest of it. The tangent function has this general shape to it. So hopefully anybody watching this video is reasonably familiar with the tangent function and what it looks like. Now, in our problem here, we're looking for an area bound between minus pi over 4 and pi over 3. So I went ahead and just roughly put these values, negative pi over 4 here, pi over 3 here. And the first thing to consider is this. There's really two different regions we have to consider. Here's the first region. And then the second region. Okay. Now, before we actually set up some work for this problem, there's an important thing to realize. The function values to the left of 0 are negative. So if we integrate some sort of area equation from minus pi over 4 to 0, we're going to get a negative value. Then if you integrate from 0 to pi over 3, you're going to get a positive value. And those two numbers are going to add to a value that does not accurately represent the bound area, because the first part of the integral is negative. So what I'm going to do is I'm going to break this into two separate integrals. One of them from minus pi over 4 to 0, and then another one from 0 to pi over 3. Now, whenever you're doing an area or volume calculation, you should always draw the differential element that you are basing your equations on. So in this case, I'm going to draw a rectangle here. I'll go ahead and draw one over on the right as well. In both cases, the width of that rectangle is dx. The length of the rectangle on the right is the function value, but on the left, the length would be minus the function value if I want the length to be a positive number, because the function values are negative on the left-hand side. So the area, and I can write this in one line, I think, the total area bound between minus pi over 4 and pi over 4, we're going to start with the first integral from minus pi over 4 to 0. If I take the function tan x times dx, that's going to give me length times width. There's the area. However, the tangent is negative in this region, so what I'm going to do is insert a minus sign to make that length positive in the region from minus pi over 4 to 0. This integral will now yield a positive value representing the area bound in this region. Now we're just going to add to that a second integral from 0 to pi over 3. The length of this rectangle is the function value, tan x. We don't need a minus sign because the tangent is positive in this region, times the width, dx. So the first important part of this problem is recognizing that we need two integrals here if we want to get that total bound area. And recognizing I need a minus sign here to make this length positive so that I get a positive area when I take this product. All right, now we'll start working on the integrals themselves. So tangent is sine over cosine. So I think what I'll do is take these integrals one at a time. Take the first one here. Minus integral from minus pi over 4 to 0. And I'm going to go ahead and write this sine x over cosine x dx. I'm going to make a substitution here. I'm going to let u equal cosine x. Double s there. All right, one s. Du would then be minus sine x dx. I'm going to go ahead and transform the limits as well. If x is equal to minus pi over 4, then u is going to equal the cosine of minus pi over 4, which is positive root 2 over 2. Remember that the cosine function is an even function. The cosine of negative pi over 4 is the same as the cosine of pi over 4. So this integral can be written, right, minus integral, let's see, from minus pi over 4 is now a root 2 over 2 to 0. Oops, oh, I forgot to do the 0. If x is equal to 0, looking right here, cosine of 0 is 1. U is equal to 1, so there's my top limit. Now, let's see. I'm going to go ahead and just do this. Minus sine x dx. This term right here, minus sine x dx. And then I look right here, minus sine x dx is equal to du. So this entire thing, minus sign included, is equal to du. So I don't need that minus sign anymore. Oops. That one can be erased, right? Over u. This is going to equal now, integral of du over u is natural log u, evaluated at these limits from root 2 over 2 to 1. So this is going to equal natural log of 1 minus natural log of root 2 over 2. Now the natural log of 1 is 0. Now at first glance, this kind of looks like, maybe there's a problem, because this comes out to be negative natural log root 2 over 2. Well, it looks like a negative number. And remember, I went through great effort to talk about how I wanted that first integral to come out positive. This term is in fact positive because root 2 over 2 is less than 1. And the logarithm of something less than 1 is a negative value. So this thing is in fact positive. We can just fix this. We can absorb this minus sign into this and write this natural log of 2 over root 2. So I'm going to go ahead and store this up here. The first integral, let's see, this thing is 2 over root 2. Natural log of 2 over root 2. All right, I'm going to take a moment here, clear my work, and work on that second integral now. Get rid of all of this that I don't want anymore. It's one of the little drawbacks of this pad here. I don't have a ton of room, but all right, I'm going to work on the second integral now. Integral 0 to pi over 3 of tan x dx, which I'm going to write sine x over cosine x dx. This one's going to be a little bit shorter, I believe, and work out nice. Again, the substitution we want to do here is let's let u equal cosine x. Therefore, du would equal minus sine x dx. Remember that the derivative of cosine is minus sine. If x is equal to 0, then u is equal to 1 because the cosine of 0 is 1. And then if x is equal to pi over 3, then u is equal to, looking right here, the cosine of pi over 3, which is 1/2. So our integral can be completely rewritten as the integral from 1 to 1/2. And I think what I'll do is take note of minus sine x dx is equal to du. And I look right here, sine x dx. I don't have the minus sign, but that's an easy fix. I'm going to go ahead and just insert a minus sign and then put another one out front. This is now identically equal to du. And then over cosine x, which is u. All right, minus signs. We can either absorb it in the limits or deal with it later. I'll just deal with it later. So minus antiderivative of du over u is natural log u, evaluated from 1 to 1/2. Now this would normally be ln of 1/2 minus ln of 1. I'm going to go ahead and absorb that into the limits and write this ln of 1 minus ln of 1/2. So again, for anybody watching this video, this term would be natural log of 1/2 minus natural log of 1. But if you absorb this into the limits, that becomes natural log of 1 minus natural log of 1/2. Natural log of 1 is 0. At first glance here, we look at this and we say, ruh-roh, Shaggy, a negative number perhaps. We're looking for an area, it should be positive. Well, the natural log of 1/2 is a negative value. So this thing is in fact a positive value. We can take this minus sign, absorb it into the logarithm here, write this natural log of 1/2 to the minus 1, which is natural log of 2. So that second area has got a magnitude of ln of 2. So I'm just going to take a moment here though, and I've got some people watching me go through this video here and ask them if they have any questions. So what do you folks think? Is there any questions about that example? Everything looking good? Good, now if there's a mistake, it's on you folks. Okay, so let me go back and kind of put this together now. Again, I'm going to get rid of stuff I don't need anymore. One more time before I delete this. Anybody have anything they'd like to ask about that thing that I sectioned off? All right, well, let's get rid of it then. So our total area, bound between, again, minus pi over 4 and plus pi over 3 and the x-axis, and y equals tan x, is the sum of these two. What do we got? Natural log of 2 over root 2 plus natural log of 2. And I think I'll just leave that right there. We could combine them, but I don't see any reason to. Suffice to say, that is some number. So, hope this video helped do a couple things. One, I hope it was a kind of a decent review about finding areas and watching things like, oh, the function value is negative on this side, so this has to be broken into two integrals. And always make sure you draw your differential elements, whether you're doing an area calculation or a volume calculation or any other type of calculation. How to work the integral. In this case, the tangent function is integrated by writing it sine over cosine and letting u equal cosine x. Hope this video helps demonstrate these things. Have a great day.